Hey all, it's Mr. Alexander, and today I want to talk to you about the paired or dependent t-test. What I have here is some data on school policy. It's a tardy policy, and the school wants to know if the policy is having any effect. They think that the new policy will reduce tardies. So what we have is the number of tardies before the policy was enacted and the number of tardies that were after. Now hopefully you can see that this is a dependent t-test because we're looking at it first period, second period, third period, fourth period, fifth period, sixth period, seventh period, eighth period. So it's dependent because we're going to compare first period to first period, second period to second period. Because first period obviously going to have more tardies than second period because people get to school late first period, but then they're there for second period. That sort of logic. So this is a dependent t-test. So the question of interest is, does the new tardy policy reduce tardies? And our two populations are the before policy, the number of tardies before policy was enacted, and the number of tardies after. So, we think that this policy will reduce tardies. So the way we write the null hypothesis here is that the mean difference, or mu sub d, equals 0. The way that the two sample dependent t-test works is we're only really going to consider one sample. We're not going to consider both of these samples individually like we did in the independent test. We're actually going to subtract these numbers, and then we're going to look at a difference. So I don't have that difference here. I'm going to get it in a second. But most of the calculations work the same as the one sample t-test. What's important to do is to define what this d stands for, what this difference is. And I think what we want to do is the number of tardies before minus the number of tardies after. So essentially I'm going to take this first column and subtract it, and subtract the second column. I got to do 252 minus 214, 143 minus 136. Now the reason that's important to define it is it's going to help me shape the alternative. Now I'm still going to have my mu sub d, my mean difference, and I'm still going to have the 0, but now I need to decide between greater than, less than, or not equal to. The way I'm going to make that decision is from my context clues in the question, and the key word being here reduce, so I think it's going to be less than. So I'm asking myself, okay, should this be less than or greater than? Well, the way you can think about it is, if we were to actually do all the subtraction, are we going to have positive numbers or negative numbers? So like 252 minus 214 is a positive number. 229 minus 199 is a positive number. So in this case, it's going to be the mean difference is greater than 0. And that's what I would expect. Now, if I was trying to do it the other way, I would have a negative. If I would have I just arbitrarily chosen to do before minus after, but I could have just as easily said after minus before. And if I had done it that way, this would be less than. And they're both equally as valid. There's no one right way to do it. We can assume random samples and independence, but I cannot assume normality. The reason why? I've only got a sample of 8 here. My sample size is less than 30. Now, that's not a big deal when I write my conclusion. That's just something I might want to address. But it's not enough for me to say, okay, I can't do this analysis. It's just something to be aware of. So if I'm going to draw the null distribution, my n equals 8. So my degrees of freedom are still going to be n minus 1, just like in the one sample t-test. So my degrees of freedom are 7. So my null distribution is going to look like this. I've got my 0. This is t. I'm going to have some value here, and here's the critical region. Now, what's that value? Well, that value comes from the t-chart. Since my degrees of freedom are 7, I'm just going to assume that my alpha level is 0.05, which you should do. You should always assume it's 0.05 unless you heard otherwise. And I'm going to use 1.895. If this was two-tailed, I'd use the 2365. But since it's the mean difference is greater than, that's one-tailed, so that's 1.943. Or sorry, that's 1.895. 1.895. So anything greater, any t-value greater than 1.895 is going to be in the rejection region. Anything less than that is going to be in the fail to reject region. So now I've got this data, right? I've got the before and after. I'm not really interested in these before and afters. What I'm really interested in is the mean difference. The easiest way I find is to go to stat edit and just quickly type into list 1, the first column here. And in list 2, type in the second column. Now, I don't particularly care about these numbers. What I'm really interested in is the mean difference. So I can quickly get the calculator to tell me that mean difference. If I highlight L3 and then do L1 minus L2, I got this L1 and this L2 by doing second 1 minus second 2. When I hit enter here, it's just going to do all the subtraction for me. So the difference then, in period 1, there was a 38 tardy difference. Period 2, there was 3 tardy difference. 21, 7, 48, negative 1, 30, and 8. So what I'd like to know, based on those difference scores, is the mean difference, the standard deviation of the difference, and the sample size, which I already know, it's 8. So, in order to get the calculator to calculate this stuff for me, I'm going to do stat calc 1, but I need to change the list to list 3, because that's where my difference scores are, and you get that list 3 by doing second 3. And so my mean difference is 19.25 tardies with a standard deviation, that's S sub x, of 17.92. I can use that standard deviation to calculate the standard error, which is the standard deviation of 17.92 divided by the square root of n. So my standard error, 17.92 divided by the square root of 8, is 6.34. Now I'm going to use that standard error to calculate my test statistic, which is the mean difference, which is 19.25, divided by the standard error, which I just calculated, 6.34. And that should be 19.25 divided by 6.34, 3.04 for my test statistic, which means I'm right here. I'm in the rejection region. That t statistic is big enough that I would reject the null hypothesis, which means that my p-value is less than 0.05, and we would say that there is evidence that evidence that the new policy is working. The new policy is reducing tardies. Now that's all well and good, but the next logical question is, well, okay, by how much? And so that's why we would create a 95% confidence interval. So we take that mean difference, 19.25, plus and minus the t critical. My degrees of freedom are still going to be 7, but now I'm going to kick it over to 0.025 because the confidence interval is inherently two-tailed. And I'm going to use my t-value, a t-critical of 2.365 instead of the 1.895 I was using before. 2.365 times the standard error of 6.34. So my confidence interval then, 19.25 plus, or I guess I should do minus 2.365 times 6.34 is 4.3 essentially, and change it to a plus, and 34.2. So how many tardies is it reducing it by? Approximately 4 to somewhere between 4 and 34 tardies per class period essentially, which is not insignificant. We show that to be significant. How can you double check all this on the calculator? Well, you've already got the data typed in, right? You go to stat edit, and the list 3 is all these different scores. Because the dependent samples t-test is just one sample, it just happens to be that the one sample comes from 2, but we're talking about different scores. Because that's true, because we're only considering the differences, in the calculator you'll just want to do what we did in the one sample t-test. You want to go to stat, tests, and then it's number 2 for the t-test. It's like it's a one sample t-test. It's calculated the exact same way. So you have a couple of choices here. You can either do data and say, hey, my data is those different scores in list 3, and I think that that mean difference is going to be greater than 0, and then calculate it. My t-statistic was 3.04, which is exactly what the calculator got. I said the p-value is less than 0.05. That's what the calculator got. And of course, here's the mean, the standard deviation, and the sample size. So this is a nice way to double check all that information. Like, oh, there's my t-value, there's the p-value, which I couldn't calculate without the calculator, by the way. RStudio can do it, but I was unable to do it on hand. Same thing if I want to get this confidence interval, this 4.3 to 34.2, stat, tests, and then it's just like we're doing a one sample t interval. So that's stat test 8. And again, you can either say that the data's there, or you can tell the statistics directly. It's already pulled the data because I told it it was all in list 3. Shouldn't make a difference. Confidence level is 95%, and they calculated a 4.3 just like I did, and a 34.2. So this is a great way. The calculator is a great help when it's a dependent samples t-test. Maybe not as helpful when it's independent samples because of the way that degrees of freedom are calculated. But for dependent samples, go ahead and use the calculator. It's going to give you a pretty close to the right answer every time. Just use it to double check, as always. Don't use it as your primary source. Okay, that's it. Thanks for watching my video on dependent samples t-test. We'll see you in a little bit for the chi-square test in the next unit.